Welcome back. Hope you enjoyed the lunch and you're enjoying the session so far. I'm really delighted to be able to introduce our next panelist. This is a really exciting topic. Quantum computing gets a lot of the attention. I think a lot of it's got to do with those chandeliers in the superconducting qubit modalities. They make for great photographs and it's very exciting. But there's some incredibly exciting stuff happening as well around the whole topic. And I think networking and cryptography is a really important part of that. So I'd like to start by allowing my colleagues to introduce themselves. And what I've asked them to do is to spend a couple of minutes just really to talk about whatever you think is pertinent in the topic at the moment, what you'd like to highlight to the audience, and then we'll move the conversation forward. So Laura, I'll hand over to you, and maybe you can introduce yourself and tell us what we should all know.
Thank you, appreciate it. My name is Laura. I'm a physicist by training, and I'm now run Qunett, which is a full networking hardware stack company. We're based in Boston. Our focus is on building scalable networking hardware solutions, so quantum routers, entanglement sources, and transducers. And I think one thing I'd like to touch on is we heard a lot about quantum computing earlier today and the great progress that's been done there. And I think really for the last decade or so, quantum computing has really been the spotlight of quantum technology. And I think very soon there's going to be more of a shift into focusing on networks. So I'm glad we're talking about this today. And I think really there's going to be sort of a market pull towards networking and just more of a shift in focus on that. And I think there's two reasons for this. One is that really quantum computers are going to need networks in order to scale up. And this is really just sort of interconnecting quantum processors in order to build up larger, more powerful quantum computers. So I would say that's one reason. And the second is that we've also talked about, high-performance computing type applications, but there's also a lot of different types of applications that revolve around sort of heterogeneous connections between different types of quantum devices. For example, quantum sensors connected to quantum computers. And I think that there's a lot of interesting applications, things we don't even know about yet, that are going to become important and interesting that quantum networks will be able to enable.
Brilliant. Okay. Looking forward to continuing the conversation. Mihir.
Right. Hello, everyone. Mihir Bhaskar. So I'm CEO and co-founder of also a quantum networking technologies startup called Lightsynq. So my background is I've actually been doing research in quantum networking broadly for over a decade now. So first as sort of a PhD in academia at Harvard. For the last 4 years or so, I actually joined AWS. I was the first hire at AWS with a sort of quantum optics and networking background. Built their strategy in the area, built an R&D team called the AWS Center for Quantum Networking here in Boston, developed some cool technologies and got very excited about it, built a thesis on how to commercialize this, and we ended up spinning that off into a startup that I now run, Lightsynq. And so the main focus of what we do, I won't talk about it too much since I want to just offer broad perspectives, but just so you know what we are doing. We're really focused on one of the core aspects that Laura mentioned, which is we have heard a lot about quantum computers needing to scale to very large sizes before they're going to be really useful and transformational. We also have a lot of exciting progress in quantum computing. So we have actual hardware that works and that's starting to be error corrected, but it still needs to scale about 3 to 4 orders of magnitude before it's really going to be practical. And so I really think networking is both the most sensible and the fastest approach to realizing that. So our focus at the company is using this decades of research in quantum networking technologies to build high-performance interconnects to scale quantum computing. Just broadly speaking, when I think about the field of quantum networking, it's quite interesting because it's useful to think about classical networks and how we use them. And I think there's an interesting quantum analog for each of these uses of classical networks. And so, we have communication, we have scalable computing, like this is how we build HPC systems. We also have global positioning systems. These are networks we use for sensing and metrology. And then we have things like cloud computing. And actually, for each of these 4 areas, if you take that information processing task and you make it quantum, so you build a quantum network, you get an interesting spin on that particular application. So I think one that we'll probably talk a lot about, since cryptography is in the title of this panel, is quantum key distribution. So in this communication task, you can use the fact that there's a theorem in quantum mechanics called the no cloning theorem. You can't take an unknown quantum state and make a copy of it. So that means if we can communicate by sending these quantum signals across a channel, we can verify that there's no eavesdropper on the channel. And so this is a concept that's been around since the 80s. So it's really one of the oldest concepts in quantum information processing, and that's quantum key distribution. And then on the other end of the spectrum, there are these scaling up quantum computers, actually interfacing quantum computers to networks and interfacing sensors over networks. We've thought about those as being some of the longest term applications of a quantum network. But I think what's quite interesting is that quantum key distribution communication has been around for a very long time, and we have companies and we're doing this at small scale. But when you think about the ordering of applications of quantum networks, I actually think that we're in an interesting place where these small scale QKD systems still exist, but the real value and interest in networking is actually starting to now combine it with quantum computers to figure out how to make them scale and how to unlock new functionality with these quantum computers over a network. And I think that's where the value is going to be over the next 5 to 10 years in quantum networking.
Brilliant. Thank you very much. Lily.
Hello, everyone. My name is Lily Chen. I'm a mathematician, and I'm a NIST fellow. And I have doing research on the cryptography. So I will talk very different topic today, and I learned a lot from this morning's session. So we talked a lot about Peter Shor, Professor Peter Shor, and from MIT. I kind of like to mention another professor. His name's Ruane Revest, and from MIT as well. So RSA is the first generation of the public key cryptography system, and it made history. And the paper was published in 1978, that time frame. And that after that, RSA has been implemented in almost every internet routers and computers, laptops, smart car, smartphones. So then after that, in 1994, and Peter Shor published a paper said with the quantum computers, full-scale quantum computers, the factorization problem is not hard anymore, and it can be solved by polynomial time. So this morning, they discussed about what that means, right? So if you think about these two things happen not in the kind of like 20 years. My work at NIST is to lead the cryptographic standards program, and we developed the standards originally for non-classified government usage, but now it's actually used by most of the digital device. So NIST cryptographic standards has been used implemented in almost every digital device. And so now for us, the most important is how to make today's cyberspace and infrastructure resistant to quantum attacks. So then we call that quantum resistant cryptography, and some people give it another name, post quantum cryptography. So we have worked on the standards for 8 years, and started 2016. We published the first set of the post quantum cryptography last year. So this is a very kind of important for the quantum time, for the cybersecurity. What I really kind of concern is that whether it's soon enough for us to implement all these standards, because NIST, actually the US government, and made 2035 as the year to move away from traditional public key cryptography like RSA. So this morning's talk, I'm trying to catch the message whether 2035 is soon enough. Thank you.
Fantastic. Yael.
Hi, guys. I'm Yael Kalai. I'm actually a professor here at MIT in CSAIL, Computer Science Department. And my research is on cryptography, mainly. Theoretical computer science, kind of more broadly. I'm a theorist at heart. I don't do my work is not, I don't work on applications, really, more of kind of the fundationals, the theory of cryptography. And as relation to quantum, so quantum has really been disruptive to our field, as kind of Lily mentioned. So in cryptography in general, we encrypt message, we digitally sign, our economy is based on this kind of integrity and secrecy. But we actually don't really know how to do that. We only know how to do that assuming there's some problem that's hard. So today, when you think you're communicating secretly, or you're signing digital messages, is it really secret? And the answer is yes, if the adversary can't solve a hard problem. Okay, we don't give unconditional results. It's only if the adversary can't solve. And now there's a question, well, is it really hard? And the answer is, we actually don't know. Okay, the only thing we can say is we don't have attacks. Now, where does this kind of elaborating a little bit on what Lily mentioned, why is quantum relevant? Because some of our schemes, such as the RSA scheme, is based on problems which actually turn out to be easy using a quantum computer. Not that we can't solve these problems today using a quantum computer, but if quantum computers will be kind of more large-scale, large-scale quantum computers, then we will be able to solve these problems and hence break our schemes. So this is a big problem for us. Okay, so now a lot of cryptography is based, as Lily said, on kind of moving away from these kind of pre-quantum assumptions that are known to be broken using quantum attacks, or assuming that problems are hard, but these problems are actually easy again, using quantum devices, to different assumptions that currently we believe, or we hope, cannot be solved or broken using a quantum device. So that's where kind of cryptography stands. And I just want to mention, actually, the problem with quantum is much more severe than that. The problem with quantum is not only that our assumptions are kind of broken using cryptography. As Lily said, now kind of all of cryptography, we're trying to upgrade it to be post-quantum secure. So we want at least the assumptions to base our cryptography on assumptions that we do not know how to solve using quantum computers, or we believe are actually hard to solve using a quantum computer. But actually, it's more than that. Like when we prove the security of our schemes, in our proofs, when we kind of argue the security, we assume that the adversary is classical in a sense. Because the way we prove the security of the scheme is we say, well, suppose there's an adversary that breaks the scheme, and we're going to use this adversary to break the problem, to kind of solve the hard problem. It's like we have reductions. So we say, if you have an adversary that breaks the scheme, I'm going to use it to break factoring, to solve factoring. And if you believe that factoring is hard, then such adversaries can't exist. But how do we do that? We take our adversary, we say, suppose there's an adversary who breaks the scheme. We're going to run him. We're going to rewind him. We kind of abuse this kind of adversary, something that cannot be done using in quantum because of kind of what you mentioned, the so-called no cloning theorem. So I guess my point I want to make is not only do we have to kind of move to post-quantum assumptions, we need to kind of make sure our schemes are actually secure, even if it is an assumption that you can't break using a quantum computer. So actually, we're kind of in a mess. And everyone is scrambling to try to upgrade cryptography. Now, for you guys, all the users of cryptography, don't worry, we got you covered, okay? We're working night and day, and it's going to be okay. But for us, it's a lot of work. That's one thing. But let me end with a positive note and say, actually, it's a very exciting time for us as well. Because if quantum computers will actually exist in large scale, and we're starting to see it even now, then actually we can use it to get our cryptography kind of much better. Okay, so that's kind of what we call quantum cryptography as opposed to post-quantum cryptography. So kind of we're dealing with both things. We're dealing with making sure our schemes are actually secure. If quantum adversaries exist, oh my God, are we okay? But we're also kind of excited to see, oh, now we all have quantum computers. That's amazing. What else can we do? So that's kind of where our field is standing right now.
Brilliant, really interesting. So many things I want to delve into. I recognize that not everybody here is a technical expert as well, so I may dig into a few of the basic concepts. And maybe I just start with, say, quantum networking. We already have networks. We have fiber optic cables, we have repeaters, we have switchers. They all work really well. Why can we not send quantum information around these same networks?
Would you like to take this, or
I'll start, and
go for it.
You can add. So the challenge with quantum information is it's very fragile. We're talking typically about like single photon type levels, and these photons are what we're sending over the network for communication. And unfortunately and fortunately, the principles of quantum mechanics sort of make it very difficult for us to develop routers and switches that also work for quantum information. So our classical routers and switches aren't going to work if we, say, measure the quantum information, we then destroy it. So we have to develop basically an entirely new hardware stack that's capable of handling this type of information. So I kind of like to think of it as ideally operating as a sort of quantum layer on top of today's internet, is how I like to think about it.
Yeah, Mihir?
Yeah, that's exactly correct. I'll just give a different spin on it. You mentioned some of these components. You mentioned fibers. You mentioned switches and routers. Fibers are great. So fibers are perfect for quantum signals. And in fact, so these optical photons, which are really kind of the smallest amount of light that you could have, where you turn down the intensity of your optical signal so that it's actually one photon at a time. These will travel great through optical fibers. So you can send a single photon through kilometers, several kilometers of optical fiber. And so you can actually build quantum technology using basically existing components if you just have a source, a fiber, and a detector. And it's on the order of tens of kilometers. And so that's really quite incredible. And that's why this field of quantum cryptography has actually been around for many, many years. Now, when you want to do something beyond just like a single channel, 2 nodes in a network, and you want to, let's say, make this much longer, or you want to have a multi-point network where you have lots of configuration, you have to go through lots of interconnects. This is where we use the switches, the routers, and things like that. Or in long-distance networks, we use repeaters. And this is where it really breaks down. You can't amplify a quantum signal. You can't take a single photon and make an amplified copy of it. So it violates this no cloning theorem. But also at the fundamental level, what it's doing is it's also adding more noise than you can tolerate. So that's just impossible. And that's where it gets really, really hard with quantum networking, where you have to have a different type of component. You need things like memories, and that's really important. You need storage in your network in order to be able to go to longer distances. We need quantum repeaters, which use this storage and use this computation to actually extend range. And so those are the components where there's a big gap between what you could have done in the 90s with what we're trying to do now to make these scalable on a data center or global scale.
Really good. What I'm consistently reminded of when I have conversations with experts like this is the difference and the incorrect way I use 2 words, hard and impossible. And when you really get into the detail around a lot of these topics, they mean different things. Mm-hmm. So you've been talking here about quantum networks and, for example, the challenges around the repeater, etc. And I might inadvertently use the word it's really, really hard, and then a quantum physicist would say impossible, and we have to try to delve into those topics. So we've been hearing about some of the breakthroughs earlier on today with quantum computing. There was a really nice breakthrough there late last year from Google. They actually had 2 really big breakthroughs. Are we seeing something similar in the networking space, where there is things that look almost impossible to the layperson, but the expert knows it's just really, really hard, and we're seeing some nice, steady progress. Can you give us a sense of where the field might be at that research?
Yeah, I can speak to that. So I don't want to give the impression that it's impossible to send quantum information around the globe. So there is such a thing as quantum repeater, and it leverages this memory. So the idea has actually been around since 1998. So we've known conceptually that, hey, you can actually do this. And it took about 22 years for us to build a system that was able to break the so-called repeaterless bound on communication, where you can communicate faster over a quantum network than you could, given the limits of loss in that network. So we now do have some of these technologies. So that's some of the stuff that we're commercializing. These quantum memories where they're at the point where they can actually extend the range of these quantum channels, or they can increase the bandwidth of these communication channels. We're just at that cusp, over the last couple of years. And so I'd say, like, the work that was done, in the Harvard labs in 2020 was kind of the equivalent of that demonstration showing for the first of a kind. There's still a big gap then, if you now want to connect the continents, right? You would need something like, tens of quantum repeater stations, and the functionality you would need in these stations is not just like one device that is, the state-of-the-art device. You need to scale that up by hundreds, and you need to improve the performance. You need some local computing power as well. So I think the challenges of building really global-scale quantum networks are kind of similar to building quantum computers, with the added factor that this has to be kind of deployable and networkable.
So for people in the audience, sorry to cut across, for people in the audience, to visualize this, are we talking about fiber optic cables going across the Atlantic to Europe and needing these repeater stations along the way? Is that the option, or is there anybody doing any work, maybe, for example, with satellite that might be interesting here as well?
Yeah, Laura, do you want to speak
to that?
Sure,
yeah. I think the fiber optic networks are really good at sort of metropolitan city-type scales. For really long distances, I think it's unlikely that repeaters are really going to be an efficient way to do that, just because of how much hardware you would need to cover such a long distance. So that's where, as you mentioned, satellites would really come in for the longer distance global scale communication.
Right. Okay. Mm-hmm. And I want to bring the conversation as well in terms of the cryptography, to give a sense as well of how this whole field has been changing so much. We've got maybe an idea for where the research has been emerging on the hardware side. But on the cryptography, Yael described it, you described it like it's really been quite a profound change within your profession. Mm-hmm. Lily, you've been talking about the NIST getting really spun up on this project in around 2016, I believe. So can you give us a sense of, in your world, how big of a deal is this? Maybe Lily? Yeah.
So how big a deal about this quantum attack to the current cybersecurity system, right?
Yes.
So I think everyone uses the VPN, right? That's you dial VPN to your enterprise network. So the current technology is like this, right? So basically, you start to to do the handshake and use the public key cryptography, like a digital signature, to authenticate each other, right? Like U.S. government use a kind of smart card called a PAVE card to authenticate to the network, and then the network authenticates to your device. And then after that, you use public key cryptography and to establish kind of like the common key. And these common keys are used to do the data encryption and authentication, because after you connected that session, then just a very fast speed data will start. Like emails is not that fast. Like a voice, audio, conference call, and these kind of things. So that's the current usage. It's almost, you can see that it's almost everywhere, right? When you dial in your bank account, or you dial in your Uber service, everything. So you use cryptography. And you use public key cryptography, no matter you are aware or not. So if all these RSA and the ECDSA, Diffie-Hellman key agreement all broken, and then this means all the network is not secure. So it is indeed a big deal, and the impact is everyone, every device, every industry, and every organization. So that's about the impact.
That sounds big to me. Yeah, great. And Yael, I hear about some of the names of these new cryptographic standards. I hear about lattice-based approaches. Can you give an incredibly complicated topic can you give the audience some sort of intuition for what we're talking about from the old approaches to the new ones?
Okay, so let me start with the story, okay? So as Lily said, we all use public key cryptography whether we know it or not. Every time you connect to Amazon, to your bank, to whatever, there's a handshake, whatever that means, that uses what's called public key cryptography. Public key cryptography today, the way it's used, is completely broken using quantum. Okay, luckily we don't have quantum yet, or for us it's lucky, for you guys maybe less, but we don't have large scale. So we all now move to assumptions, in particular lattice-based assumptions, that whatever the math behind it is, let me shove it aside. But these assumptions, we believe, we hope, are post-quantum. And in particular, there's one kind of flagship assumption that's considered the most kind of sturdy, secure assumption in this space. It's called learning with error, okay, LWE. Basically, if I had to give an intuition of what it is, it basically says the following. If you have linear equations, it's easy to solve them. Linear is easy, even by classical computers. It turns out if you have a linear equation, but they're noisy, it's hard to solve them, we believe. And we also believe it's hard to solve them using quantum computers. So now we are kind of upgrading all our crypto to be secure against these assumptions. The assumption that says it's hard to solve kind of noisy linear equations. Now my story. About a year ago, so every time we write a paper, like, oh, my paper is based on LWE, a post-quantum secure assumption. Okay. So last year, around this time maybe, a paper is put in the archive saying quantum attack against LWE. That's the title. Was submitted to a conference. My colleague was reviewing it. Actually, the entire, cryptographers, like all our community, sat together, tried to understand this damn paper. We're all freaking out, of course. I remember that time I had like 3 papers submitting to that conference, all of them kind of, security against LWE. And now they have another paper saying LWE is broken, okay? And long story short, there was actually a bug in that paper, so it was retracted. However, it had darn good ideas in it too. So, is LWE indeed post-quantum secure or not? Frankly, I don't know. We don't have an attack, but it seemed like he had some good ideas towards an attack. Still kind of no one has been able to get the attack, kind of push it through all the way. But you're asking how disruptive is it to our to our community, our cryptographers. We're panicking, actually, because even the post-quantum assumptions we have, I don't know if they're secure or not. And kind of that paper was just one example that got us kind of freaked out. So we're really, and now there's a lot of other types of assumptions that we're trying. So of course, one of the things we're now scrambling is, okay, let's have as many assumptions as possible. So if one breaks, we'll have an alternative. Because currently it's like everything, lattices. I don't know, maybe yes, maybe no. And so we're now a lot of our work is trying to expand the space of assumptions, also maybe other lattice-based assumptions, and maybe isogeny-based assumptions. Anyway, there's all these kind of assumptions that we're trying to look into and basically hedge our bets.
Can I make a poorly informed statement, and I want you to critique it and tell me why it's wrong, and maybe Lily, you can get involved as well, is that I've understood that we need move on from our current encryption standards. It's a really big deal. NIST, through the work Lily, you and others have led, have come up with a handful, maybe 3 or so, algorithms that can do the heavy lifting. But fundamentally, they're really taking a lattice-based approach. Mm-hmm. But we don't know of a way the lattice-based approach can be broken, but we don't know for sure that it's impossible. Would that be fair?
Yeah, 100%. And let me tell you, so NIST has done an amazing job, really. So kudos to you of standardizing our stuff. If today I or any leading cryptographer would have to standardize something, they would standardize a lattice-based system because that's the best we have right now. But can we say, oh, we have lattice-based, we can relax? No, we're really not relaxed. And my guess is that NIST will have a lot more work to do on trying to standardize more things because I feel like our field is again in some freak out mode of, let's try to get many assumptions, let's try to get many schemes. How do we deal with this monster that, again, it can be a good one or a bad one of quantum.
Well, Lily, so what we've heard here is you've done all this incredible work. You're taking kind of a lattice-based approach. Mm-hmm. You've issued these new cryptographic standards. You're telling people here who are running businesses or, are running industries to take this new approach and build it into their entire stack, everything from hardware to software and everything in between. Mm-hmm. And Yael is telling me that they might change their mind next week.
That's correct. Yes.
And that we'll finish the. Yeah. No. Okay. Yeah. Tell us more. What else can we do?
So I can give another kind of announcement. In March 11, NIST announced another selection on the key encapsulation algorithm. It's not lattice-based. It's code-based called HQC. So we are trying to diversify our portfolio about the next generation of the public key cryptography to make sure that we have enough resistance to the quantum attacks.
Right. I hear the phrase agility a lot. Mm-hmm. What are people talking about, and how does it relate to these different algorithmic families?
So actually the agility, so a lot of people ask me this question, what is the definition about the crypto agility? As a mathematician, I like definitions a lot. However, there's no cross-board definition about the crypto agility. It means different things. For the protocols, crypto agility means Alice and Bob can negotiate their cipher switch and to make it work. So that is interoperability. That means each of them have several options. Then finally they can agree on something to use and to establish a secure channel to talk. And this is about the protocols. And also for the computing platform, today a lot of applications relies on software libraries, APIs, and hardware accelerators to do the cryptography. That means the applications can choose different crypto systems, right? For enterprise, right, the IT administration, they need to understand what they are currently used. If something happens, if something is broken, where this will start to stop to use those bad algorithms and to replace new one without interruption. Today's world cannot afford to stop the internet for 2 seconds, for 2 minutes or something. So that is about the crypto agility. Because people talk about the crypto agility, think, oh yeah, we need that for the PQC transition. But I would like to say that is beyond the PQC transition. So the PQC transition is not the first transition, and I'm sure it's not the last transition. So we need to make our cyber ecosystem a jail to all the attacks. We need to have the crypto agility in each of the implementation environment. That's a kind of something I want to say about the crypto agility.
I want to come back to the networks in a minute, but I've got one quick question that would help me understand as well the complexity of this. So we're saying that an enormous body of work for industry and academia, etc., to switch over to this new group of algorithms, but actually we need to be dynamic and be able to switch out if Yael comes up with a new one next week. Can you give us a sense of the overhead on devices and implementing these new type of cryptographic standards? Can everything be run on my watch? Is it different from my iPad? Is it different if I'm running a secure data center for the government? Are all these approaches equal in the same way as our current standards are? I don't know, Yael, or maybe you.
Well, I think Lily's more of an expert on that than I'm. I'm more of a theorist, but I'm sure things are not equal. Like some things are more efficient, some things are less efficient. For example, symmetric encryption, where you just share a key, not like this public key variant, is much more efficient, whether it's post-quantum or not post-quantum. And that's why today we do the public key only to agree on a secret key. And then we do symmetric cryptography. So each algorithm actually, some are more efficient, some are less efficient. And it seems to me that currently the post-quantum are less efficient. I don't know, otherwise we would use like lattice-based today. Why are we waiting if it's more efficient? We're waiting because it's probably not as efficient, but it's not clear if it's going to be noticeably inefficient. And so I'll let Lily take it.
Yeah, that's quite right. Yeah, of course, if we have option, we certainly will select the most efficient algorithms, right? But we don't. We want to have the crypto agility. We want to have a backup. So think about that small piece of a chip. It's a small kind of device. You need to implement multiple algorithms. That certainly is a burden for the implementation, right? We have the resource limit, and the cryptography, and especially post-quantum cryptography, the most challenge is about the bandwidth, because they have larger public keys, larger digital signatures, and larger ciphertext. That will really challenge those kind of systems, if they have the bandwidth limitation. Even like IP network, they exceeded the maximum package size. They need to truncate, segment, and reinstall, and that will delay the communication, right? So another point is that the crypto agility, you want to be more secure. However, remember, this is a double-edged sword. Because you introduce complexity, right? The complexity is the enemy of the security. And when you have more options, basically you open a wider surface for the attackers. So that is the crypto agility is not for free. It's an expensive practice. This is not what we want to, is we have to.
Our colleagues at the end of the row are giving us nothing but bad news. Tell me something that might happen in the next 5 years in quantum networking that's getting you excited. Laura.
I think that there's a lot of great work being done at various test beds around the US, and I think it's really exciting to start to see early stage prototypes of some of these systems being deployed on those networks. And I'm hoping, we can sort of see some of these use cases really come to fruition there.
So give us a sense of that on a practical level. We talked at the very start of the day, we talked a little bit about these test beds. So like physically, what do they look like? Who's working on them? Is there a big building here at MIT and it's taken over by this big network, or is it everything underground? Give a sense of the physicality of this.
Yeah, we do have a test bed in Boston. Do you want to talk more about that?
Yeah, sure. So there's a test bed in Boston that actually has been around for many, many years, and it connects various points. A couple of the points of relevance would be, Harvard campus to MIT campus to MIT Lincoln Labs, and so, one of the test beds, in this case, it's more of an academic research test bed, and it was very recently used to show for the first time that you could, we've probably talked and heard a little bit about entanglement today. We think of that in a quantum computer as, this is like a chip or a small system where there's some funky quantum state that you have, locally in that chip. And so what we managed to use this testbed for was to actually connect 2 points over a 35-kilometer fiber and show that these, over this 35-kilometer fiber, we could actually have entanglement distributed, right? And this is where quantum mechanics gets weird, and you start thinking about things like spooky action at a distance. So that's where we are. That was a paper that was published in 2024. So that's where we are today. We're able to now take these concepts that Einstein kind of dreamed about, many, many decades ago, and put them into practice at this scale where we can actually deploy this over fibers that are run under the ground that are leased, from Crown Castle, which is a telecommunications provider in the city. Yeah. So that's an exciting point in time, but it's still a few steps away from, a practical application of using that. And I think that's what's exciting over the next 5 years in quantum networking is we have these more advanced systems, we have some of these test beds, and we have some emerging quantum computing and sensing technologies that we can actually connect to these networks. Mm-hmm. And now we'll be, taking some of these very far out ideas that we've had for a long time, where we've thought, in the field when I joined, this requires the intersection of quantum networks, quantum computers, and quantum sensors. This is never going to happen. And now we have the test beds, and we have the first technologies. We even have some companies that are actually building them at larger and larger scale, and we're going to see these components connected and used in new ways. And so that's, I think, what's very exciting over the next handful of years. Like, will it generate billions of dollars of revenue in the next 5 years? No, I think that's overly optimistic.
None of your investors are in the room, right?
None of the investors are in the room, but this is also, a level setting with the investors. This is a long-term, deep tech endeavor. But we're going to, for the first time, do these transformational things that you can't do in classical technology, right? And so that's really, really exciting, and that's what motivates further investment to scale these technologies up.
That's really important. We've seen that with plenty of other technologies as well, where the core, maybe invention or whatever, needs all these complementary innovations as well, and how important that is for the whole ecosystem to grow. Mihir, you've been talking there a little bit then about what you're looking at it as a startup. But Laura, can you guys talk a little bit about that? Like, what is it like running a quantum startup, even in somewhere like Kendall Square, general area, coming out of places like MIT or Harvard? Surely it's a lot easier for you here, and it's easy to raise money because everybody's raising money in quantum today, and it's everybody is winning. Is that right? Is that how it's going?
Oh gosh, if only. I think Mihir touched on this a bit, but I think, the timeline to a very large return on investment for quantum networks is far out. So I think that brings challenges on the investment side. So it's the level setting with investors and making sure they have an appetite for risk and a very long-term time horizon for the return on investment that they're looking for, and making sure that is agreed upon and established.
Yeah, and I can speak from my experience. So I mentioned this. We had this kind of breakthrough demonstration in 2020 where we showed you could extend the range of this channel, and I was just coming out of grad school at the time, and in 2020, Google had just published their quantum supremacy result. The field was hot. Investors were throwing money at this. There were a bunch of tier 1 VC firms that hadn't yet made a bet in quantum, and everyone wanted to do it. So we could have raised a lot of money to build, some sort of quantum. We didn't know what we were going to do with it, but we could have raised a lot of money at that point to build a company. But the prevailing sentiment I was hearing at the time from the investing community and from the industry was that we would have practical applications of large-scale quantum computers and networks by 2025. I think it's 2025 now, right? And so what we've seen is we've made a lot of progress. We should be excited. I don't want to pour cold water on the whole field. I'm incredibly excited about the progress we've made, but it's still we're still a few steps away, right? So my experience having we raised a Series A round and closed it in November. So my experience with that is that going out and talking to investors this time around, 4 years later, everybody knows about quantum and its challenges, and many people have made investments, have then used those investments to learn about the field and the challenges. And so the investing landscape is a lot, they still have a lot to learn, but it's a lot more intelligent, and there are now investors that are kind of looking at further horizons. The other thing that's different that I'm particularly excited about, and this is where I think we're going to see a lot of exciting companies and a lot of progress, is there's a lot of capital that's been poured into building quantum computing, software and networking systems now. And there's an entire industry within quantum that requires a supply chain of all of these new components that actually don't exist. So we have, that's why we exist as a company, because people have built quantum computers. They're starting to become good, but now they need to connect them together to scale them up, right? And even in that interconnect, right? You have loss, and so we need new solutions. We need new materials. We need new, optical connector technology. So some of the first products we're bringing to market are actually these component technologies that are, we're going to be able to sell along the way to help advance the quantum computing roadmap. And so, in terms of what's it like running a startup, it's not just going to that end goal of building this large-scale system, but it's charting the course of how to build valuable technologies and generate value along the way. And I think that's what's really exciting, and the ecosystem here in Boston, with all of the great innovations out of Harvard and MIT and the other institutions, is a great place to be.
Yeah, it's interesting. Even at this conference, I'm starting now to meet investors who specialize in quantum. Right, that just didn't even happen until a couple of years ago, and how international it is as well. Kendall Square and Harvard, MIT, etc., is a real focus point, but it is not the only place in the world that's doing this work. I want to elevate the conversation. Andy did it earlier on this morning. I think it's important as well. We've been talking about technology and whatever, but let's throw some geopolitics into the conversation as well. I will not insult anybody by asking who's winning, China or America. I think we all know that's a conversation that in itself doesn't have a simple answer. But can you give us some context as to the areas where you're specializing in individually or whatever? To give us some context of what you think is important that's happening at the, in the international sphere, what governments are getting really interested in all these things. You're all broadly in the business of keeping information secure. I can't think of any government who doesn't care about that. So what are you seeing in quantum networks in Europe or in China at the geopolitics level?
Yeah, I would say there's a lot of investment in QKD in Europe. So there's been a lot of progress made there and a lot of already deployed commercial solutions there, less so in the US. But I think there's going to be a shift towards more networking solutions in the US and really focused on an entanglement distribution across those networks.
And what is it that why are the Europeans locked on QKD?
That is
what is it? What is it even for a start?
Yeah, I can answer that one. It's actually a pretty interesting and controversial geopolitical topic, which is for many years the national security, the NSA at the U.S. has had a very negative stance towards quantum key distribution, and they have some very valid concerns about the maturity of the technology and potential backdoors and current implementations. And so I won't go into all the details, but if anyone's interested, just Google NSA quantum key distribution or quantum cryptography, and you'll see their list.
Do people still Google, or you just ChatGPT for that?
I don't actually know what ChatGPT would say.
Okay.
NSA has a web page that comes up if you Google it, or I don't know, Bing or whatever search engine you want to use. And so that's actually had I think the recommendations that are made there are directed at production systems, don't be rolling this out on your production systems. But that's also had a profound impact on the research community, because it's hard to get grant money and fund your research motivated to build QKD systems. And so it just has naturally had this effect where the QKD industry in Europe, which doesn't have historically has not had this phenomenon really built up. They built up a supply chain and components. And also in China, where I would say that there's the most advanced demonstrations of quantum key distribution, have really been built up, and they weren't really built up here. And what was instead invested in here are these more advanced technologies of entanglement distribution, the types of things that I've talked about, which I think are also very, very interesting and exciting. But that's probably the most interesting geopolitical topic when it comes to quantum networking. Yep. And I think also I should say there are trends in Europe now that we're seeing where they're also starting to sour on QKD.
Yeah.
So it'll be something to watch over the next year or two.
And the satellite thing with China, what should we know about that?
It's incredibly impressive technology, and I think the main thing
I should have prefaced, what is it first, and then why should we care?
Yeah, so China has carried out a number of pioneering demonstrations over satellite to show that you can actually you can launch a satellite with optical communications technology, and you can actually connect, build a quantum network to connect points that are thousands of kilometers, I think up to 5,000 kilometers apart. Which, as I mentioned, you can't really do this over the fiber networks. Laura pointed that out very, very nicely. And so, like, what it tells me is there is a practical route forward if you do want to connect these positions. And a lot of advanced technologies have been developed there in China. It's not clear that those technologies exist elsewhere, but I'm not an expert enough to comment on that.
Interesting. Lily, we move the conversation to you. I know you are a government employee, so we'll be respectful of that in terms of what you can actually comment on. But here's a basic question. Does China have an equivalent of NIST? Are they developing their own standards, or is the world waiting for America to take the lead?
Well, we saw a kind of news report about China to publicly announce that they are going to have people to submit the Post Quantum Cryptography. However, they have certain kind of requirements, but when I tried, I couldn't see the requirements. Maybe that they have their own kind of like something equivalent to IACR, but this is only China membership based. Maybe I guess that's not available for the others. So, but that's for the Post Quantum Cryptography, but not for QKD.
And so elsewhere, then it really does seem like NIST has taken the lead with this. The U.S. government, you speak to its decision around enforcing people who supply software and hardware to the U.S. government needing to implement your new standards.
Well, I think there's another way to say this. So NIST has a FIPS 140 validation program. This validation is validate crypto module, hardware module, or software module, right? So this only the device with validated module can supply to the non-national security government usage. For example, I have a NIST issued laptop. That laptop has the crypto module part has to be validated by the FIPS 140 validation program. So that side is that not to say the vendor has to, vendor or software, hardware vendor have to implement NIST cryptographic standards. It's like if they supply to the government, they will need to implement NIST cryptographic standards and get the validation through the FIPS 140 program.
Yeah, and in doing so, this is likely to kind of force these vendors through this system, and then they're likely to give it to everybody else as well. Is that a right way to think about it?
It's not like NIST first the vendors. It's usually right now we work a lot with vendors. For example, when we do the algorithm level, we work with the research kind of community like IACR, or cryptographers. Thousands of people join this kind of the whole thing and to do. But for the implementation, we work with other standard organizations. For example, like IETF, Internet Engineering Task Force, for the like IP security and application layer security. We work with some other like a TCG, Trusted Computing Group, and these kind of things. So to help them to say, okay, you can use the cryptography, NIST standardized cryptography this way or that way, or they will tell us why they cannot use something and what made them difficult to implement or something. So it's kind of like a two-way communication with vendors.
Yeah,
I would say that way.
I want to say one more thing about NIST, just to add to what Lily said. Actually, I think you guys are doing it really brilliantly, because the way it's done, at least from an academic perspective, when they want to upgrade their schemes, they have this competition. Okay, that people can submit a scheme. And as a result, what happens is this competition, people submit schemes, they submit the best schemes they can, but moreover, because they want to win, they try to attack other people's schemes. So they get it like this free kind of competition thing among people. They have the best minds trying to, break the other scheme. Like, why would anyone have the incentive to do it? But they somehow manage to get the incentives exactly right. And I think so I don't think the way to think about it is like, U.S. government are like choosing the schemes for us. They are choosing it, but it's a very much corporative, like between academics and others. And so it's really kind of a collaboration, I would say. That's how I view it. And about the geopolitical scene and how I experience it as an academic, my experience is a bit different. I feel like if you want to get money easily, do AI. A lot of us actually our research a little bit shifted, not just because of funding, but just because it's interesting. And it relates to cryptography in the sense that, that we have the new kid in the block, these LLMs. How do we ensure they're doing what they're supposed to? How do we ensure it's safe? How do we ensure it's security and so on? So there's a lot of new questions that kind of arise from this. And for me, that's my biggest kind of how the geopolitical situation kind of affects my research or the research of my colleagues.
Really interesting. It lends itself to the last question I'm going to ask. But just before I do ask that, I want to say that we're going to open the room up for Q&A. So if you've got any questions that are bubbling up, we'll give you a chance to ask them in a second. And I think we've got microphone runners. So who's ever ready to ask some questions, you please pop up. But I think the last question I want to ask is by far the most important question of the day, which is, as it relates to quantum networks and quantum cryptography, what will the impact on Bitcoin be? I think that's the question that everybody wants to ask. Is there any impact or none, or this is just something that's just noise out there and it's just another use case? Who'd like to take a crack at that one?
Let me ask you what the question is, because when you say Bitcoin, do you actually mean Bitcoin or do you mean cryptocurrency?
Cryptocurrency.
Okay, so if you mean cryptocurrency, today so cryptocurrency is based on crypto, and a lot of the crypto, they use at least Bitcoin, definitely, in other companies as well, or cryptocurrencies, are based on digital signatures that are currently broken using quantum computers. However, they can upgrade themselves as well. So once NIST will actually implement their post-quantum schemes, I'm pretty sure that everyone will upgrade, including these cryptocurrency companies. So the disruptive on them is exactly like the disruption on all of them.
And it's no different at a fundamental level. So Lily will save the day for Bitcoin.
Lily will save the day for all of us.
Oh, good. So that's worth a round of applause. I agree. Great. So questions. Who's got their hand up? Yes, here in front of us. And we'll go down there.
Thank you. I'm Jack Arrier. I'm an IT and cybersecurity professional. My question is, what can I do as IT and cybersecurity professional to prepare my organization now to make the transition to post-quantum cryptography? What can we do to prepare for the inevitable future when our crypto is broken?
That is a very good question. I can take that question. And there's a unit called NCCOE. It's a long name, and in NIST. And they have one project, migration to PQC. They have a series of the publications, special publication 1838 A or B or C, about the organization, how they prepare your organization to make such a migration. And you can also participate this project as a collaborator and work with others and propose some your ideas and things there in the NCCOE.
A great question. I hear one that's been asked a lot in industry today, and I think a lot of opportunities for startups and vendors and experts to get in on this conversation. So thank you. Jason, I see your hand up.
So there's a lot of things in cryptography we want beyond communication and authentication, such as zero-knowledge proofs, homeomorphic encryption, program obfuscation. Is there anything that we knew how to do with RSA techniques that we don't know how to do with post-quantum cryptography?
So yes, but the question, so there are things that today we know how to do using assumptions that are known to be broken with quantum and we don't know how to alleviate to be post-quantum. One example of that is program obfuscation. So that's one good example. However, let me say that the way we know how to do program obfuscation in the pre-quantum world is so inefficient. It's really a theoretical curiosity at this point. It's way very, very far from the way it's implemented in practice is really not the way like academics or based on like a cryptographic assumption. It's just a heuristic, the way people do it in practice. I think if you think about practical applications, like things that we actually use, the answer is no. And let me even say more than that. Fully homomorphic encryption, which you brought up, which is a really interesting primitive that is starting to get used at least to some extent. We know how to do it using lattice-based cryptography, and we don't know how to do it under any other assumptions except lattice-based, except this LW assumption that I mentioned. So I guess to answer the question, today we're not stuck. We're not in a point where we're stuck with primitives that we only know pre-quantum assumption. That's not a bottleneck for us. Great question. Thanks.
Great. Other questions? This gentleman here, and then go down there.
Thank you. I'm Benito, representing the fellow startup, and we talked about the VC dialogue that has to go on between the quantum technology startup and the investors. And I kind of heard that it's a whole different kind of dialogue, right? I mean, so the question would be, does it require a different kind of VC to actually do meaningful quantum technology investment, or can any big VC just learn it and do it?
That's a good question. I guess I'll take that one. I don't know that it requires like a special type of person, but I think investing in quantum technologies is generally not aligned with like standard VC fund models where they have a certain fund lifetime, they need to return capital over a certain, maybe they have a 5-year period and a certain target, and there's just math that then drives the incentives of how when they invest, then they would expect to see, the growth for their companies, right? And so I think this quantum is not the only thing for which this is the case. This is a general deep tech investing challenge, and especially in these kind of like hardware technologies where you're taking something from the lab, you need to, it's been validated in the lab, now you need to validate it at scale, and then you need to manufacture it, and you have to solve the sort of product market fit, right? So it's not just quantum that has that problem. So I would say there are some investors that are more excited about that challenge, that have different fund models, and like those are the ones that are the most interesting to talk to and are most engaged with quantum. But I don't think it's like a one-size-fits-all answer.
Happy?
I don't have anything else to add there.
Good. Carl.
Yeah, so we have 2 physicists and 2 mathematicians. At the end of the day, in the long term, is physics going to protect us and our knowledge of using those systems, or is it going to be the math that protects us and makes us secure in the future?
It's funny. I don't distinguish that much between the two. Physics and math, it's hard for me to even say how to draw the line between physics and math.
Yeah, I mean, I can take this one since this is not what I'm actively working, but have done some research in this. And, so I think you're kind of asking about quantum key distribution. And ultimately, instead of using these mathematical cryptographic primitives, would we one day want to upgrade to quantum key distribution and use that as the ultimate, end-all, be-all? And I think in general, the answer is not going to be that like just the physics of a device is what protects your sort of information. You're going to have many layers, and that may be one of them. So that's my first answer. The second answer is the ultimate realization of this like physics-based information security, where you use like some law of physics, right, like the no cloning theorem or the properties of entanglement to guarantee the security of your channel. When you implement it in the lab, you have these real devices, and these devices could have backdoors, and there could be issues that are actually related to the physics of the devices. And the most prominent example of that is the photon detectors that you use to detect the signals over an optical channel. When you detect one of these single photons, there's actually a little pulse of light that the detector inadvertently emits that actually can couple back into the fiber and can be measured. So this is actually a known attack on some of these systems. So actually, it's the physics of the devices themselves leads to some vulnerabilities. And actually, the ultimate realization of this quantum key distribution is something called device-independent quantum key distribution. And what it actually is like mathematical concepts at the end of the day that you're verifying and checking to make this maximally secure. So I think it's always going to ultimately be math, even if you use these more advanced technologies to secure your channel.
Yeah, what I want to say is both is probably what you'll need in collaboration and together.
You didn't get a physicist's answer or a mathematician's answer. You got an academic's answer, which is both. Yeah, great. One last question. I saw one hand there back.
Hi, so there's been some talk recently of using quantum technology to create certified randomness. And JP Morgan recently did a demonstration using Quantinuum's, one of their quantum computer prototypes to create, I think, 70,000 bits of certified randomness. How important is this to cryptography generally, and are there real applications?
So it's a hard question. It seems like we always use a random number generator in our machines. It's implemented. And there are actually, it should work well, and it does work well, except when you don't use it well. So it is true that currently, sometimes when you hear of attacks, sometimes it is due to bad randomness. But often I feel like it's due to bad randomness because it's not used correctly. I think the classical way of generating randomness, of course, it's not real randomness. So, okay, let me tell you the difference. The difference is they actually generate randomness. Okay, quantum can generate randomness. We, using math, generate pseudo-randomness. What does pseudo-randomness mean? It's not random at all, but nobody can distinguish. So it looks, for practical purposes, it's random. And that's good enough. The only catch is sometimes people mess it up in implementation, and they don't use it well. And then it's a problem. But if you use it well, the fact that we can't generate randomness out of thin air because, I don't know, it's just not possible. You need actually quantum for that. That's not actually a real threat to cryptography because we have good ways of generating pseudo-randomness. That's good enough in practice. Yeah, unless, Lily, do you have a different perspective on
this? Sometimes when you do the pseudo-random number generator, you need a seed.
Right.
The seeds are true random number, right?
Yeah.
So for the NIST current the validation, they call that entropy source, right? The entropy source actually can be everything. You can use the quantum entropy source, actually. As long as you can pass those testing and to say this is a qualified entropy source, then it will be a qualified entropy source.
Well, fantastic. I think we'll leave it there in the interest of time. I'm sure I say on behalf of everybody here, we really appreciate you taking the time, but also I've learned a lot from listening to you this afternoon. It's really rare to get such experts who can talk across so many different areas of a very complicated domain and be able to bring it to life so well. So thank you very much. Thank you.
Thank you. Thank you.
We're going to take a break now until 3 p.m. and then